Okay, so we are recording the session now. I'll just share my screen. Those who had a problem yesterday with the Bloom box test results, could you resolve it? Could you figure out what went wrong? Could you all figure out what it was, what the problem was? I'm guessing those people haven't joined in yet.
Ma'am, are you talking about that mismatch of values?
Yes.
No, ma'am, we couldn't.
Are you one of those people? Yeah.
Yes, ma'am.
Okay, so which version of R are you using? R Studio?
Ma'am,
That might be,
4.0.2.
okay, let's see. Maybe it's an older version, so that might be the issue. So you can just update it, all right? What about the rest of the results? In yesterday's session, the rest of the results were the same. Only that particular test was different, is it?
No, ma'am, the rest of the results were also coming out a little bit different.
Little bit, or because the last one, your conclusion was completely different from our conclusion.
I'll have to run again and check, ma'am.
Okay, fine. Okay, just if you're encountering the same problem today also, then just do it, continue doing it, but just keep cross-checking with our results. Okay, so I'm sharing my screen so you can check what is printed on my screen, and I'll be discussing based on that. If anyone else gets different results, just let me know. So just before we start, there was one thing that I want to show you. Okay, so yesterday I was telling you something about the characteristic roots and so on. So just go through this. Okay, I've written it down for you all. Okay, when we were using this auto plot, for example, in brackets, if you put mod 4 or mod 3, okay, we use this command and then it showed us a graph of that unit circle, okay, where you have a graph with the y-axis being a set of imaginary numbers, x-axis as real numbers, and then they plotted the unit circle and showed that all the inverse characteristic roots were within the unit circle. Okay, so regarding that, I was trying to explain to you all what was meant over there. Okay. So this is how, if you have an AR1 model, okay, and you solve the complementary function part of it, okay, you'll find that B is equal to 0.5. Just go through it quickly. Okay, now B is less than 1, even the absolute value of B is less than 1. Okay, so B is known as the characteristic root, and this particular equation here, which is in brackets, B minus 0.5, it is known as the characteristic equation. Okay, so we set it equal to 0 and then solve for B. So that is how we generally find the characteristic roots of any difference equation. Now, since B, the absolute value of B is less than 1, okay, it lies within the unit circle. So if you plot this circle with a radius of 1 on that graph, okay, you'll find that B lies within that unit circle. Now, for the same AR1 model, okay, if you use the lag operator and then write the model, okay, so this will be the representation of the same model. So now this part becomes our characteristic equation, okay, 1 minus 0.5 L, where L is the lag operator. So here, if you solve for L, you'll get L is equal to 2, which is the inverse of B. Okay? So L is referred to as the inverse characteristic root. Okay? Now the characteristic roots for any stationary time series or process, you'll find that the characteristic roots have to lie within the unit circle. Okay? And if you look at the inverse characteristic roots, the condition will be that the inverse characteristic roots should lie outside the unit circle if this particular time series is stationary. Okay? So we generally refer to these two conditions, and that is what the plot is showing. But in R, they use the opposite terminology. Okay, so they are referring to L. Okay, they are probably writing the entire model when it's in the form of code using the lag operator. So they refer to that as the characteristic root, and hence the plot shows B. Okay, where B will here be referred to as the inverse characteristic roots, and the inverse characteristic roots will now lie within the unit circle. Okay. So they are just using the opposite sort of terminology to refer to the two things. Generally, we refer to L as the inverse characteristic root. So those should lie outside the unit circle. Okay. And B, which are the characteristic roots in the terminology that we have learned. And this is the general terminology followed everywhere. B is the characteristic root. So the characteristic root should lie within the unit circle. Okay, but generally, because it's easier to plot these roots lying within the unit circle, what they show is B. Okay, and they refer to as it as the inverse characteristic roots in R. Okay, so it's just the opposite terminology being used. So I just wanted to clarify that, because if somebody goes back and looks at what we have learned, you might get a little confused and you might wonder what's happening. I hope you all have understood this part. Any doubts or questions here? Okay, since you all don't seem to have any doubts or questions, we'll just continue, okay, with where we had stopped yesterday. So yesterday we had estimated these models, right? Okay, we had estimated model 1, 2, 3, and 4. And then we were comparing these models based on the statistical significance of the coefficients, okay, the t values of the coefficients, and the AIC. Okay. We are, for now, let's just stick to using the AIC or the AICC, okay, where AICC is the corrected archaic information criterion. I think it's corrected for degrees of freedom. I'll try and confirm that by the next class. Okay. So we were comparing these 4 different models using these criteria. Okay. And mainly we were focusing on the model selection criteria, AIC or AICC. Okay. I would prefer to use that since we have only 132 observations in our sample right now. Okay. So based on these models, just compare these 4 models. I hope the results are there in front of you on your own screen. So just compare these, and based on the, let's say, AICC, which is the best fitting model, just go through it on your own screen. Okay, mine is only showing AIC right now. So I'll compare my models using that. Anyone can,
Ma'am, the lesser the better, right?
yeah, you want to minimize the value of AIC or AICC. Yes, anyone?
Model 3 was
Okay. So model 3 is the one. Is it the same for AICC if you're using AICC?
Yes, ma'am. If you use AICC also, model 3 is giving us the least.
Okay. So based on our results, Okay, we are finding that model 3 gives us the best fit. So we can just save the specification, okay, of this model. It's an ARIMA 202 and 011, okay, 12 model. So we'll just save that specification. You can just copy it from above if you want. Yeah, I'm writing 12 because there are 12 seasonal observations in a year, okay, since we have monthly data. Or there are 12 seasonal periods in a particular year. Yeah, I've saved the AIC value also. You can save the AICC also, okay, where it's, if you find that that information is available to you. So right now, this is giving us the best fit. Okay, so I had said yesterday that uh, you might find this entire process tiring and frustrating, okay, because you have to keep trying to estimate the model based on trial and error, okay, and then find the best fitting model. So this time we've just estimated 4 models, but we can probably keep refining it further and further till we get the best fitting model. So we might end up estimating more than 4 models, okay, but for now uh, we'll just switch to the shortcut method, okay, which allows us to estimate very quickly and with minimal effort what the best fitting ARIMA model would be. Okay, so the command for that in R, okay, is auto ARIMA, auto.arima. So let's just call our model now model 5 and use that command, which will help us to estimate very quickly. Okay, so R goes through various models step by step. There's an algorithm which was developed by somebody named Hinman and Khandakar or something like that, 2008. Yeah, can't pronounce the names very well. So they came up with an algorithm which helps you sift through various models and then select, R automatically selects the best fitting model for you. Okay, so the specification or the command that you'll use is auto.arima, then the name of the time series. Okay, remember that for us, I think it was BTLY1. Based on what you have saved it as, you can go ahead and put that in. Now, when you're typing this, okay, suppose you type here auto arima. So this will start prompting you. Okay, so you can depend on R to kind of prompt you and help you remember the commands. Now the default is generally set as stepwise equals false. Stepwise equals true. So we'll set it to false. Okay, so stepwise means that in the algorithm we have a couple of steps which have been outlined. So it looks at a particular model first. For example, a 0D0 model. Okay, so I'm specifying the order of PDQ, the small PD and Q. So it might sift through that model first, and then it will switch to a 2D2 model, okay, and then it will proceed that way. Okay, so there are about 4-5 models that it goes through, and then it selects the one which is the best fitting model out of those, and then it probably reduces or increases the autoregressive and moving average parameters by 1, and then proceeds that way to select the best fitting model. Okay, so it's a stepwise process. But if you set stepwise to false and even approximation, okay, to false, then it'll just make our work a little harder to find your model. Okay, otherwise the search is quite fast and you get your results very quickly, but it might not look through all the possible models. So if you set stepwise equals false and approximation equals false, which are basically some kind of shortcuts again within this algorithm itself. So if you set that equal to false, then it will cover a wider range of models and then you'll be able to select the best fitting model. Okay, so right now let's do this and run the command.
Does this command
Oh,
take
sorry.
more time to run?
No, not very much. Okay, since
Because
our data set is not that large. Okay, so and we do have time, so it won't take that long. You'll just have to load your library. I haven't done that. Okay, so just load all the packages into the library and then you can proceed.
ma'am, the AICC is coming larger than Model 3. I think Model 3 is still doing a better job.
Okay. Okay, so I'm guessing the results did not take long since you already saw the AIC value. Okay, now generally when R is using any algorithm or stepwise procedure like this, okay, you'll see that R is still at work if you see this symbol here. Okay? And once this disappears, then you'll be able to get your results.
Ma'am, you mentioned that you had 132 observations in your data set. Can you
Yes.
show that code again, where it was written 132 in the console?
Mm,
In the
here,
console,
see.
there was a table, I guess, X132, because I think I'm
I
getting 126 observations. That is why there's a difference
okay,
in value.
okay, fine.
Vibhor, maybe when you omitted your values, probably you might have omitted those is NA while trying to do that.
Also, I'm not able to get that table that you got.
Which table?
Where 132 was written, observation 132.
See
In the console
DTLY
only.
one. Okay, this one you're not able to get.
I'm in the console. Can you go above?
Just a minute.
Uh, Down. Yes, ma'am, this table.
This
Yeah.
this is not important. Okay, it's just related to model 2. So it's just telling me what are the things that I can access from model 2.
Okay.
This is not important. You can just type the same command. Are you able to get it?
Print summary mode. Wait. No, ma'am, I'm not getting a table.
It's not looking like this.
No,
But
ma'am.
don't worry about it. For example, I'll just show you. You don't have to type this. If I just do this, okay, so I can access any of these. For example, if I want the AICC from model 2, okay, I can just type this, hit enter, it will return the AICC value for model 2. Okay, so if I just want to extract some information from my model, I can use this operator, okay, this dollar sign, and then type whatever it is I want to access. R will prompt you. It will show you what are the things that are available, what is the information that is captured in that model, and then you can select whichever one you want and then look at that.
Yes, ma'am. In my data set, it's showing 126 observations. That is why there's a difference in AICC value.
Okay, okay. Try and figure out why that happened, okay? later. Yeah,
Already.
so let's look at the results from model 5. You all might have already done that. So if you look at it, Auto Arima has selected a 400 model. So 4 non-seasonal autoregressive terms are there, and you have one order of seasonal differencing, one seasonal moving average term. Okay. Now, are all these significant? Somebody asked a good question right at the beginning of the class. So yesterday I was telling you that you have to take the coefficient value divided by the standard error, and the value should be greater than 2. Okay, so consider that the absolute value should be greater than 2. Okay, then your coefficient is significant. So here, if you look at it, I think AR2 is not significant. Okay, whereas the rest are significant. Okay, now if you look at the AICC value, okay, what you will find is it is minus 683, and even the AIC is minus 684. So our model seems to have done better. Okay, remember this is an algorithm. So maybe by chance we have beaten the algorithm this time. Okay. Just give me a second. Go through your results. Anyone has got different results?
Ma'am, the model has been described as the same 400,011,12, but my AICC is coming as minus 655.07.
Okay.
I think maybe I might have omitted some observations, and maybe
You'll be able to see here in the
yes,
environment
ma'am, in
part,
the
right?
environment.
Do you have the same number of observations?
DTLY1 has 126 observations.
Okay, that's why I guess. DTLY1 has 126. Okay, strange. Anyone else has the same information? DTLY1 has
Yes, ma'am.
126. Everyone, is it?
Yes,
ma'am.
Ma'am, maybe while running the codes today, you may have not used the is NA code, NA dot
Oh,
omit
yes.
code.
Yeah. Correct. Correct. Yeah. But I think I had saved DTLY1 as, wait, let's
ma'am.
see.
But yesterday also you were getting 132 observations as well.
Yeah. Just give me a minute. No, it's nothing to do with the missing observations.
Okay,
I
ma'am,
don't,
I'll just restart my R code again from the top.
No, I'm getting the same values what you are getting.
okay. Fine. I don't know what the issue is, why y'all are having 126 observations. Okay, so we'll try and figure it out. Don't worry about it. But just continue the same way, okay? Just type in the commands, continue the same way. Maybe in the 5-minute break that I give you, maybe you can try and restart it or something like that. Okay, so now let's see. This is the result produced by Auto Arima. Let's again use these commands. Okay, so auto plot mod 5. So this will show you a plot of that unit circle. Okay, all the roots are within the unit circle, so our model looks fine. Okay, then again we need to do the diagnostic checking of the residuals. We want our residuals to be white noise basically. If you looked at the significance of the coefficients, I'm sorry, my cursor seems to be acting up a little. So if you looked at the significance of the coefficients, you will find that only AR2 is insignificant in this model. Okay? The rest will be significant, the rest of the coefficients. So use the command check residuals to check the residuals from your model. Okay, so the residuals appear to be normally distributed. There's a slight spike here, but maybe you can ignore it. Okay. But the Lune box test is telling us that our residuals are free from autocorrelation, okay, at various lags. So this model appears to be fine, model 5, okay, that we got using auto arima. If you want, just run the command again. Okay, this time just omit this part. Okay. So the default is stepwise is equal to 2 and approximation is equal to true. You need not enter that. So just try running this command again and see what results you get. Let's see if they're different. Okay, so this time it's selected a different model. Okay. You can see because it hasn't done the stepwise search. I mean, it has done the stepwise search, sorry, in this case. So you found that this time it selected a model with 2 non-seasonal MA terms and this seasonal part is the same. Okay. And if you look at the significance of the coefficients, this time all are looking to be significant. Okay. And the AICC value is minus 678.19. It looks like we're still doing better. Okay, compared to auto arima, we still seem to be doing better in terms of the AICC. And this saved this information. Okay. You can just copy that entire thing from there. Okay, let's compare it with the results that we got from our own estimation. Okay. So we found that model 3 was the best fitting model, right? Okay, so except for MA2, all the other coefficients I think are significant. Okay, and this is, wait, I'll try and get it from there.
Ma'am, just sorry to disturb you.
Yes.
Just one request.
Hmm.
Uh, the line of code where you define DTLY, could you please just show that line once?
Just a minute. I don't have it here because I had saved the previous session and I'm working with that. Okay, but basically DTLY is LY minus from your decompose part. Okay,
All
we
right.
had
So
done
I
TS
think
decompose.
in my LY code I might have made a slight something with the parameters I might have changed and might have made a small error in that.
Okay. Just I'll just quickly copy the AICC value from model 3 and then we can proceed. Okay, I don't have AICC, I'm just copying AIC. So I'm just entering that information. This was AIC actually, not AICC. So our model seems to be doing better in terms of the fact that the AICC value is lesser. Okay, we have minimized the AICC value further compared to the model selected by AutoArima. But one thing you'll notice is that the AutoArima command has produced a more parsimonious model in terms of the fact that the number of the number of coefficients which have been estimated are lesser, fewer compared to ours. So generally when we model, we want a model with the minimum value of AIC, but we also want our model to be parsimonious. Okay, we don't want to unnecessarily put in too many coefficients into our model. So maybe we can go with the AutoArima result itself. Okay, this will again depend on what is the particular criterion that you're using to select the model that you want. Do you want a parsimonious model, or do you want the model with the lowest value of AICC, or do you want to select the model based on its forecasting capability, which again we'll see in a little bit. Okay, by the end of this class, we'll try and select the model based on the forecasting capability of the model. Okay. So I hope all of you have been able to follow so far. Any issues or any problems? Any doubts? Okay, nobody seems to have any doubts or questions, so we'll proceed. Okay, now, right at the beginning, when we started this whole exercise of doing practicals, if you remember, I had shown you the data set air passengers and I had shown you a bunch of code, okay, which had appeared along with the information about the data set. So the way that this time series was modeled, this data on air passengers, it was done in a particular way and differencing was used to make the time series stationary. Okay, here when we did it, we noticed that there was a strong trend, and because of that, we detrended the data and then checked the stationarity. We found it was stationary, and then we continued modeling that way. Okay, but let's do it in the way that Box and Jenkins had originally done it. So this data is from their textbook, and it's based on a very famous model which uh, they use to model the data on air passengers in the US. Okay, so let's do it their way, and then we'll do a bit of forecasting using their model itself. Okay, since it's a classic model, let's follow their methodology itself. So here we are using Ly itself, that is the time series. We are not taking the detrended series. Okay, so let's see if I have Ly here. Yeah. So this is the log of the air passengers data to the base 10. Okay, you've taken log to the base 10 on the air passengers data, and that is what Ly is. Now R already knows that it's a time series. Now let's quickly just plot the series. We have done it before in our previous sessions. Okay, but let's just do it again. So here again, once you plot the time series, you can see a strong seasonal pattern. You can see there appears to be a trend in the data. Okay? And just based on a visual exploration, you'll probably think that the time series is not stationary. Okay? So if you remember, we had run this command. I think we already tested it in the previous session. We just run this stationarity test once. So the null of the augmented Dickey-Fuller test is that the time series is non-stationary. Okay, and the alternative hypothesis is that it is stationary. So let's quickly run this test, see whether a time series is stationary or not. Okay, so based on the test, what we are finding is that the time series is, you're rejecting the null and you're finding that the time series is stationary. Are all of you getting this result?
Ma'am, I'm just confused. Why are they saying it's stationary? It visually does not seem like it's stationary. So, are they going to use differencing or?
Yeah, next we'll be using differencing. Okay, so this, has everyone got this result?
Yes, ma'am.
One minute, ma'am.
If you look at the p-value, it allows, since you've got a low p-value, okay, so you can reject the null at the 5% level of significance.
Yes, ma'am. Same.
Okay, and let's just confirm this again, okay, because we still have a doubt whether this time series is stationary or not. So we'll do the KPSS test. Here we can see that the trend is there. Okay, so we still have a doubt whether this time series is stationary or not. So let's just confirm with another test. Okay. So here the null is that the time series is stationary. Okay. But this time, instead of putting trend stationary, let's put level stationary. Okay. Last time I had asked you to put trend stationary, you remember. So let's just check this. Okay, so the null hypothesis is that the time series is level stationary, and based on the p-value, you can reject the null, okay, that the time series is level stationary. So when we are saying level stationary, it means that the time series as it is, if you take the log of the air passenger data, the time series as it is not stationary based on the results from the KPSS test. Okay. Now, if you get a result like this, when you check for level stationarity, then you can check if the time series is different stationary. Okay, so many times when you find that a time series is non-stationary in levels, if you difference the time series, which means if you take the first difference of the time series, you might find that the data becomes stationary after differencing. Okay, so this is another technique to use, to remove the trend. Instead of detrending the data that the way we did, okay, this is another technique to remove the trend. Okay, so let's try this time, since this is the method which Box and Jenkins used for their own data set. Okay. So here, let's define a new variable. Or, okay, there's no need to define it, because later when we are estimating a Riemann, the commands itself will do the differencing work for us. Okay. So just type KPSS Ly, the difference of Ly. Okay, this time, since we want to test if the first difference is stationary. So when I'm writing difference Ly, you're just taking yt minus 1, or the change in yt, you're checking if that is stationary or not. Okay. Again, type level, okay, because this time you're checking if the difference of Ly is stationary or not. The variable as it is, once you difference it, is it stationary or not, or do you need to difference it further? Okay, that's what you're trying to check. That's why you're typing level for the null hypothesis. Okay. So this time, once you run the test, you'll find that the p-value is quite high. Okay. So here you're not able to reject the null, and the null is that the time series difference of Ly is level stationary. Okay. So you found that once you take the first differences of this data, the time series becomes stationary, so you do not need to difference it further. Okay. So we've been able to remove the trend by taking the difference of this air passenger data, first difference. Okay, later, I don't know if it will be possible in today's class, but in the next class, we'll discuss which method is better. Should we detrend the data? Should we difference it? We'll discuss those technicalities in the next class. Okay, all of you understood up to this point?
Ma'am, can you later on just tell us what the KPSS test, like how it works?
Yeah. I wanted to do a separate class on the unit root test. So apart from ADF, there are at least two others that we need to discuss. Okay, so I'll have a separate session for that itself.
Excuse me, ma'am.
Yes.
Ma'am, sorry, but could you please just tell once again that why, what is this level means in the second last code, KPSS of test,
Okay.
when where we are checking level stationarity?
When you're differencing the data, is it?
I mean, the the term level stationarity means, what does it mean?
Okay. So this is Ly, right? If you look at the plot, this is Ly as it is. This is the air passenger data as it is. Now you want to check whether this time series is stationary in levels, which means as it is, without any sort of differencing, without any manipulation of this data, is it stationary or not? Okay, now just looking at it visually, you'll see that there's a trend in the data, right? Okay, and there are seasonal patterns, but you can clearly see the trend in the data. Okay, so you're guessing just based on a visual examination that it is not stationary. Okay, the mean does not appear to be constant. So when I'm saying level, this time series Ly, which is the log of the air passenger data, if I'm saying that it is non-stationary in levels, it means that when I'm looking at it this way, okay, the data as it is, I want to determine whether it's stationary or not. Now the KPSS test has told me that the data is non-stationary in levels. Okay. Now, once I difference the data, okay, I want to check whether that is stationary or not. If I take the first difference, I'll just show you the plot, then maybe you'll understand better. So if you plot the first difference of this data, see here, this is what the data now looks like. Okay, once you have taken the first difference. So from this, just by visually examining it, you can see that it is appearing to be stationary. Okay, and then we confirm it by running the test. So here again, when I'm putting level, okay, in the null hypothesis, when I'm writing this, okay, this is the command for that. Sorry, here. Okay, when I'm taking the difference of the air passenger data and then I'm checking as it is in the form of first differences, is this data stationary or not? Okay. Now, if I had found here, I'm finding that the data becomes stationary. Okay. The null hypothesis is that it is stationary as it is. That's what level means. So when I take the first difference of Ly, that is stationary in this form. Okay, in the form that the data is in right now, it is stationary. Suppose it was not stationary, then I would have had to difference it again to make it stationary. Okay.
Yes, ma'am.
Okay.
But ma'am, in the initial code of ADF dot test, that's where also we try to check for the same, right?
Yes. Okay, but here, if you look at the ADF test, uh, okay, it seems like the length of the command seems more or less the same, but the command is very limited in its scope. Okay, that's something you might notice. We are not specifying, is it in levels, is it in trend form. Okay, for KPSS, you also have the trend alternative here. Okay, here it is just whether it's stationary, or if you don't choose stationary, it is that the time series is explosive, which means that your null will become that the time series is stationary. Okay? You'll understand this better once I discuss the tests of stationarity, but just think right now that the ADF test in this form, using the current packages that we have loaded, it's somewhat limited in its scope. Okay, so it might not be able to help us determine whether the time series is stationary in levels or is it stationary in first difference form and so on. Okay? It
Yes.
might not be as what do you say, rich in terms of the options available to us compared to the KPSS test. You'll understand better once I discuss these tests in greater detail. Okay, but for now, just think that KPSS is generally considered to have better power and performance compared to ADF. And in terms of the scope that it gives us to test a particular time series, it is wider in its scope. Okay, for
Yes,
now,
ma'am.
I
Thank you.
hope that answer will satisfy you. When we discuss
Ye-
in greater detail, you'll understand better.
Yes, ma'am.
Okay,
Yes.
so
Thank you, ma'am.
here in first difference form itself, in this form, we have found that the data is stationary. That's why we're putting level here. Okay. Here you don't see any sort of trend, and the variance seems to be more or less constant. Okay, so we'll go with this result that probably a first difference of the data will produce a stationary time series. So remember that we'll discuss this again probably in the next class, but there are two ways to remove the trend from a time series. Okay, one method is that you remove the trend. Okay, one method is the way we did. Okay, but that's also not very good in some sense because we've lost quite a number of observations. We lost 12 observations. Okay, so there are other methods which I'll discuss again in the next class. Then the second method to remove the trend would be differencing the data. And I'll discuss again when we should use a particular method. Okay, but most of the time people difference the data and that makes the data stationary. Okay. So here let's take the differences and then model the data. Then again, if you look at this plot, okay, there appear to be some seasonal patterns even in this data. Okay, you can see that, right? Okay, for each of these observations, okay, for example, if this is 1959, if that is the part which pertains to 1959, it seems very similar to this part. Okay, excuse me. Yeah, so it seems very similar to this part which relates to 1960 or 1961. Okay, so there seems to still be some sort of a seasonal pattern in the data. So we might need to seasonally difference the data also. Okay. Now, one shortcut again that we can use here, which R allows us to use, is to find out directly how many times we have to difference the data to make it stationary. Okay. So if you type this command, you're basically asking R, how many times should I difference my data to make it stationary? Since we found that the data was not stationary in levels, okay, if you took Ly as it is, log of the air passenger data, we found that it was not stationary in levels. So maybe we need to difference the data. Okay, so to find out how many times you have to difference the data to make it stationary, let's just use this command and hit enter. Okay, so R is telling you that you need to difference your data once, okay, to make it stationary. Now, again, because of the seasonal patterns that we see, we might want to know whether we need to seasonally difference our data again. Okay. So you can use this command. R is prompting you, okay, which command that you need to use. So you can use this. Again, R is telling you that the number of seasonal differences should be 1. Okay, so you need to take
Ma'am,
at least one seasonal difference to make your data stationary. Yes?
ma'am, so I had this doubt. When it comes to, let's say we want to take multiple differences, let's say we want to take a third difference,
Hmm.
then will we write DIFF bracket open, DIFF bracket open, DIFF bracket open ly, or is there a more convenient way of writing a third difference?
Uh, I think this, if you write diff and then the name of the variable, comma, for example, if you want the second difference 2, yeah, I think that will do the trick.
All
But
right.
generally, we don't need more than one difference most of the time. It's very rare that you'll need a second difference or a third difference. Okay,
Yes,
so,
ma'am, I understand that, but
yeah.
should always.
So I think that should do the trick for you. So here it's telling us that we need to difference the data at least once, non-seasonal differencing, and at least one order of seasonal differencing. Okay. So let's do that and then plot our data and look at the ACF, PACF. Then later we'll use AutoArima. Okay, so let's do this quickly. Since you all know the commands, keep doing it as I'm doing it. Try and remember and do it for yourself. Okay, so first, let's take the seasonal difference first. Sometimes you need not difference the data or take a first difference if your data becomes stationary after the seasonal differencing. Okay, so it's better to do the seasonal differencing first. So the way we'll do it is, since you have monthly data, this is something we had done yesterday also. Just specify that you want to take yt minus 12. Okay, that is the difference you want. You want to seasonally difference your data once. Okay, so this command does that, yt minus 12. Okay. Now let's just plot the data and look at it. Okay, so this was our data initially, ly, a plot of ly. Now after the seasonal differencing, okay, this is what it looks like now, our data. Okay, so it still appears to be non-stationary in some sense, so maybe we need to take another difference. Okay. So let's do that and then look at the data again. So here you're taking a first difference of the seasonal
Ma'am,
difference.
just a doubt.
Yes.
SDLY difference bracket open ly comma lag 12 basically means we are subtracting today's value from a value that is 12 months before it instead
Yes.
of the t minus 1. Is that what is happening?
Yes.
All right, ma'am.
Okay. So if you have an observation from January 2021, you're subtracting January 2021 minus January 2020. So that's what you're doing. Okay, so just take the first difference of the seasonal difference now and then plot that data. Yeah, I've put the name as VDLY to indicate that it's a double difference. We took one seasonal difference and then one non-seasonal difference. Okay, so now if you look at a plot of the data, it appears to be stationary. Okay. So we'll work with this and let's just plot the ACF and PACF.
Can you do in any sequence, or you first do seasonal and then?
You can do it in any sequence, but it's recommended that you do the seasonal differencing first because sometimes that makes the data stationary, and then you can go in for the non-seasonal differencing if it's
Okay,
not stationary.
thanks.
Okay, so let's just plot the data again, the ACF and the PACF. Okay, I hope you all have typed in this command that will produce a plot of the data, the ACF and the PACF. Oh, I'm sorry. When you're typing in this command, we want to plot the ACF and PACF for the difference data, okay, not for the data as it is. So do it for the difference data. Okay. Then look at your plot. If anyone wants me to slow down or wait, just let me know.
Yes, ma'am. Could you please slow down? Ma'am, I thought we decided that we aren't going with the lag 12. So have we made any changes from that?
I didn't follow your question.
I'm not sure, but I thought you mentioned that we should not go with the difference of lag 12. I'm a little confused as to what are we doing right now.
Okay, I'll just type it out here. First, we took the seasonal difference because we saw or observed that there were seasonal patterns in our data. So if you look at this, we can see there are clear seasonal patterns, right? The same pattern seems to repeat itself every year. Okay? So that is a seasonal pattern. So to eliminate that, we were assuming that maybe once we get rid of the seasonal pattern by seasonal differencing, maybe our time series will become stationary. Okay, so we took the seasonal difference here. Okay, so this command
So, ma'am,
was the seasonal difference.
can we do a KPSS test on SDLY before we move ahead?
Ma'am, I ran the KPSS test on SDLY and our time series has become stationary.
See, again, the problem here is that since you're looking for the seasonal, what do you say? Okay, the way that I'll put it, you'll understand better again once I discuss it maybe in the next class. KPSS might not be able to capture the seasonal differencing required, okay? Because there are seasonal unit root tests again. Okay, so there are tests of stationarity which are also known as unit root tests. Then there are seasonal unit root tests. Okay, so KPSS might not be really able to capture the seasonal component of it in terms of the fact that there might be a seasonal unit root. So when I'm saying seasonal unit root, if you take the seasonal part of the equation, okay, let's see. Okay, so this part was the non-seasonal part. Okay, if you look at it, this part is the seasonal differencing part. Okay. So here, this is our characteristic equation or inverse characteristic equation. Now, if you solve for the roots of this, okay, we want the roots. I'm telling it in the general sense. Okay, we want the roots to be outside the unit circle. So in this particular case, the data that we have, it's very likely that you will find that the unit roots are within the unit circle, okay, which means that there's seasonal non-stationarity here. Okay, it gets very complicated if I discuss it, but for now, just take my word for it that it will not be able to capture whether you need seasonal differencing or not. In this test, okay, it is using these sort of tests, but it may not be that powerful to capture the seasonal differencing aspect of it. Okay, what we can do is once, maybe next week, we'll try and run the seasonal unit root tests on this. Okay, and then we can look at whether it needs seasonal differencing again or not. Is that okay?
Yes, ma'am.
See, the problem that I am encountering right now is that if I do too much theory, you all will get very tired. Okay, so I'm trying to do the practical simultaneously, but I can't cover everything. Okay, so if I had waited to cover tests of stationarity and then do ARIMA modeling, it would have taken another couple of classes. Okay, so since you all wanted to do practical work, it will make more sense to you if you do the practical work. That's why I haven't covered test of stationarity. But once I cover that, you will understand better. Okay? So for now, just I hope you'll be a little more patient till we cover that aspect, and then you'll understand better. Okay, that's the best that I can do for the moment. Yeah, so run this command and just look at the plot. We'll take a quick break, all right? It's 3:38. Let's take a quick break. And then we'll meet again in 5 minutes. Okay, so let's meet at 3:42 or 3:43. Okay, let's meet in 5 minutes, and meanwhile you can look at a plot of the ACF and PACF and try to determine the order of the model. Okay. I hope you all are back.
Yes, ma'am.
Okay, just take a look at the ACF and PACF, okay, for DDLY, that is the doubly difference data, and then try and determine the order of the ARIMA model that you want to fit. Okay. Would anyone like to share any thoughts on this? What is the order of the ARIMA model that you would want to fit? Try and guess it without running auto ARIMA. You can use the guidelines which we
Ma'am,
used
only one,
yesterday.
I think.
One of what?
You're asking for the P, Q, and D values, right?
Yes.
So, ma'am, P value, I think.
Just P and Q, since we've already done the differencing part, and then we're looking at the plot. Okay. So P, yes.
Ma'am, one value is going to be 1 and one value is going to be, I think, 4.
4 moving average, is it? You're saying?
I'm a little confused about that. One is P and one is Q.
Okay, which is P?
I don't
Look
know,
at
ma'am.
the ACF to determine the moving average part, and the PACF for the AR part.
So,
Okay,
ma'am,
non-seasonal.
I think P will become 3 because either 3 or 2 because uh, I'm not sure if we'll count 2 because it is not statistically significant.
Okay.
But it's still turning around at 2, at 1 and 2.
Okay, so looking at the PACF, you're trying to determine the AR order. Okay, so the first lag.
Oh, ma'am, sorry, ma'am, I was looking at ACF.
Okay. Okay, just look at the PACF and trying to determine the AR order. Now there's a spike at lag 1, right? Sharp spike. Now the second lag, it's very minimal. This is 3, 4, 6, 7, 9, 10, 11, 12. Yeah. So the third lag, there's a slight spike, but very likely we can ignore it. Okay. This is very mildly significant. So there's one sharp spike at lag 1. Okay. So maybe we can start with an AR order of 1. What about the MA order? Anyone has any thoughts? Non-seasonal part I'm talking about. You can go through the guidelines that I shared with you yesterday. Yeah, I'm showing you the seasonal part of it so that you can determine that. Non-seasonal, I think you all might be comfortable by now. Anyone
0.
non-seasonal? Non-seasonal MA order, you're saying?
Yes, ma'am.
But isn't there a sharp spike here at lag 1, and then there appears to be decay? Okay.
Right.
It's oscillating, but there is decay. So maybe we can go with 1, okay, for the MA order, or at the most 2, since this is still coming out of the band confidence intervals. Okay, so maybe we can start with MA2, okay, and AR1. Okay. So non-seasonal part, let's do 1, 1, 2. Okay. What about the seasonal part? Anyone has any thoughts?
I'm 1 at max.
Okay, why are you saying that? 1 AR or MA, seasonal?
I'm AR.
Okay, why are you saying 1 AR?
Maybe because there's only one lag way which is going upwards.
Okay, but if you look at these rules, okay, so they are saying if the autocorrelation of the appropriately difference series is positive at lag s, where s is the number of periods in a season, then consider adding an SAR term to the model. If it's negative, then you add an SMA term. Okay, so look at the seasonal lag now. Look at the seasonal part of it. So the seasonal lag will be lag 12, lag 24, lag 36. Okay. So here we see a negative spike at lag 12. No? So we should probably consider adding a SMA term. Okay, here. Is that fine? You all are able to follow how we are doing this?
Yes, ma'am.
Anyone has another, a different opinion to offer or any other ideas about what the order should be for the model? Okay, let's go with, see, MA, since the decay is beginning after lag 1, we'll go with one non-seasonal MA term. Okay. Remember, the decay should begin after lag q. Okay, so that's how you will determine the MA order of the process. Then for the AR order, since there's a sharp spike here at lag 1, okay, so that also we can start with, for the non-seasonal part, 1, 1, 1. Okay, we can start with that. For the seasonal part, let's start with 0, 1, and 1. Okay, let's try that to begin with, and then we can look at other specifications, okay, based on the fit of our model. So let's try that first. So I'm putting this as B mod 1, okay, to indicate that we're going to use differencing for our model now. So again, the command will be arima with a capital A, then the name of the variable. Okay, so you have to take the variable ly, because arima itself or R will do the differencing for you. Okay, so you need not put ddly or sdly as the dependent variable for your model. Then type in the order that you want for your model. First, the non-seasonal order, we wanted it to be 1, 1, 1. Okay. And then for the seasonal part, we wanted it to be, I think, 0, 1, and 1. Okay. So let's try and estimate this, and then look at the results. Okay. We can include a constant also. Let's try that. So let's look at the summary of our model. Oh, sorry, I put mod 1. Okay, it should be D mod 1. So once you've got the results, just type in your findings, okay? Okay, don't look at my screen, look at your own screen and try and determine which coefficients are significant. Anyone who's finished, you can share your thoughts with the class.
And both of them are coming out to be significant.
Which both of them?
No, MA1 and SMA1.
Okay, fine. So that's what I've typed in my own R interface, and I've saved the AICC value. Okay, so it's minus 700.1. So from this model, we found that the AR1 coefficient is insignificant. Okay? And MA1 and SMA1, that's the seasonal MA and non-seasonal MA, coefficients have turned out to be significant. So let's try and fit another model and then compare the two models, okay, and see which one is doing better. So for the next model, could you all suggest what we need to do? Okay. Based on what we did in the previous class, I think you all will be able to guess what we can do. So anyone has any suggestions? What can we do next?
Ma'am, maybe include more terms, but it's already in.
We can take 24 lakhs now.
24 lakhs of what?
I think he means seasonal, so that.
Yeah, but there's no spike at lakh 24 anywhere. See, there's no
Ma'am, I was thinking we can increase our MA terms.
two. How many?
Three or four terms.
Are you basing that on the ACF?
Ma'am, actually, I get a little confused. I'm basing that on the PACF.
No, use
Ma'am, I'm so sorry. I don't mean MA. I mean
AR.
AR. I think we can increase our AR terms from the PACF.
Okay, so instead of one, you want to add one more, is it?
Yes, ma'am. We can probably add the third and the fourth, or third maybe.
Okay, AR3. Okay, since this is 2 and this is 3. Okay, fine. Let's try that next. So instead of typing out the entire command, you can just use the up arrow button. Okay, so that will help you go through the list of commands you've already typed. Now change the name of your model to, let's say, 2. Okay, and we want 3 autoregressive terms, right? Now the rest of it, we want it to be the same. Now the reason that the constant has not been included, I think because we've done 2 seasonal differences. Okay, so R does not allow you to include a constant when you've done a double differencing procedure. Okay, so we can just drop that part of the command completely. So let's estimate this model and check the results. Okay, so you can see the results from the second model. Okay, we forgot to check the residuals or do the diagnostic checking for the first model. Okay, so just do that also. Okay, first model appears to be fine from the diagnostic checks. Okay, second model, let's see. Second model also appears to be fine based on the diagnostic tests. Okay, what about the significance of the coefficients from the second model? Can anyone tell me which coefficients are significant?
Ma'am, AR2 is definitely not significant.
Okay.
Ma'am, again, MA1 and SMA1 are significant.
Okay. Yeah. Okay, just you need not pull out your calculator and check every time. You'll get a vague idea. For example, 24 by 32 is definitely going to be lesser than 2, okay, in absolute value. So just by visually looking at it, sometimes you'll be able to understand which is significant, which is not. Okay. So MA1, SMA1 are significant. Okay, the rest are insignificant. So can anyone suggest what we can do next? If you look at the AIC value, now it's higher compared to the previous model. Okay? So maybe we are moving in the wrong direction.
I think maybe our AR direction was wrong.
Okay. But it was a valid guess because you saw a spike at the third lag, okay, in the PACF. So it's not wrong. We generally do it this way itself. You'll keep experimenting till you get it right.
Ma'am, is there a chance, ma'am, we can drop our AR1 and AR2 terms and just keep our AR3 or something of that sort? Is there a certain way of doing that?
Yes, I think there is, but I'll have to learn the command and I'll teach you that in the next class. Okay? But since the third lag, if you look at the plot, it's very mildly significant here. Okay, so you might not want to include lag 3, you might just want to keep lag 1. Okay, so when you're trying to guess which model would be appropriate, maybe you can move that way. Okay, looking at which has a bigger spike and then including that. But we had included AR1 only earlier, so that did not work. Okay, so can anyone suggest any other specification for our model? Maybe adding in more AR terms is leading us away from the best fitting model. So what else can we do? You can always set some coefficients to 0. Okay, for example, in the PDQ order, you can set any of those to 0. That is also fine. Anyone?
Ma'am, we can just set the AR equals to 0 in case, because when we are increasing it, so we are moving away.
Okay, yes. Okay, so let's try that now. Since the AR coefficients are turning out to be insignificant in every case, maybe you don't need that term at all. Okay, so this is for D mod 2. I'm just saving the results. Okay, when you're saving the results or writing comments for yourself, you might also want to include the diagnostic tech results. Okay. So I've written residuals appear okay for myself. Okay. So you can include some comment like that for yourself to help you understand. So this time when we are estimating the model, you all can go ahead and do this. Just eliminate the AR terms altogether. Okay. So the non-seasonal AR component, let's set it to 0 and then see what result we are getting now. Okay. So I'm calling this D mod 3, the third model that we are estimating. Right. So once you've finished estimating, just see which coefficients are significant, do the diagnostic checking of your residuals. And anyone just share your conclusions. Okay, anyone can share your conclusions.
Can you show the code for D mode 3 again?
Yes.
Okay, ma'am, thank you.
This model is better than D mod 2.
Yes. And it's better than D mod 1 also. If you look at the AIC value, you find that it's better than the other two models. Okay, what about the coefficients? Are they significant?
Yes, ma'am, they're significant.
Okay.
Yes, ma'am, both are significant.
Okay. So before we go any further, this is the model which Box and Jenkins had estimated. Okay. So this is that classic model which they estimated. We can check using auto ARIMA also, which is the best fitting model. So let's quickly try that and see what result it gives us. Mm. Okay, so the result has come fairly quickly. Once you finish estimating, check the residuals again. Okay.
Ma'am, in this check residual diagram, what all are we checking for?
If you look at the plot, the residual should be more or less
Centered around zero.
normally distributed, yes. Okay. Then this ACF, you should not have any significant autocorrelations. Although at lag 23, there appears to be a significant autocorrelation, but it could be pure chance. Okay, because if you look at the results from the Leung-Box test, it's showing you that none of the residual autocorrelations up to lag 24 are significant. Okay. So you can base your conclusions on this. Otherwise, if you want to focus on this, then you could try estimating another model and checking. Okay. But since this is the format of the model itself, and I think you'll have understood the technique, so we can stop here. Okay. And I'm saying format of the model, this is the actual model which Box and Jenkins estimated for this data. Okay. So this is known as the airline model, this particular specification. If you look at auto ARIMA, it's selected the same model, okay, as the last model that we estimated, model 3, I think. Yeah. Okay. So there could be small discrepancies in the values of the estimates, okay? But more or less you'll find the same conclusion. Both the coefficients are significant. Then the residuals appear to be fine. The AIC value is also very similar to the one that we estimated. So this is the model that they used. I'll just show you quickly. Okay? So if you look at the code from their model, you'll find that this is the one that they used. So when you're typing this, I had shown you this last time also. Okay? So this, if you hold your cursor on that prompt, it shows you this the classic Box and Jenkins airline data, and it describes the data. Okay? Then if you hit enter here, you'll be able to see what the data is. Okay, and they've also included the code for the data. So here again, they've estimated the model this way. Okay, so they've taken the log to minimize the variance. Then they have 0, 1, 1. This is the non-seasonal part. Then for the seasonal part also, they've taken 0, 1, 1. Okay, so this is the entire code. So you can type in or copy paste this code later on and run the commands, and you'll probably get the same results. So I hope you all have understood this whole technique of ARIMA modeling. There will be some guesswork involved based on the ACF, PACF. Okay, so I would encourage you all to guess on your own and not use the auto arima command immediately. Okay, try and get better at it so that you're able to decide for yourself instead of allowing R to decide for you. Okay, then again, we might want to forecast the model. Any questions or any doubts so far?
Ma'am, one question.
Yes.
Yesterday and in the beginning when we did the same exercise, same data, the auto arima and the AR factor
Yes.
looked significant in the way there I think we took the detrended data,
Yes.
and here we took the first difference, right?
Yes.
That's the only difference between the two.
Yes. One thing you can do is estimate that detrended model, but this time include the same number of observations. Okay, so when I was doing it, I had 132 observations for that detrended data. I think starting from 1949 July, okay, the 7th month of 1949 up to I don't know, the last 6 months were omitted. So I can use the same data set and then estimate using detrended data so that I can compare these two models. Okay, if I use, for example, in this model, we've just used differencing. In detrending, we lost 12 observations, whereas in differencing, we are losing fewer observations here. Okay, since we are taking one seasonal difference and then I think one first difference. Okay, so compared to the detrending method, we are losing fewer observations. And again, so that might make our model non-comparable. Okay, so you'll need to use the model on the same data, which means the time period should be the same. Then you can compare the performance of the two models and see which one gives you a better fit in terms of the AIC or AICC.
Then, we know the translation is already there. We know the translator is there. And then we have 2 or 3.
Somebody's saying something. The voice is very distorted. Somebody else had a doubt or question?
Ma'am,
Yes.
ma'am, I have a doubt. Ma'am, this Zoom box test, it is for checking whether the error terms are white noise or not.
Yes.
Okay.
If you remember, for white noise error terms, the autocorrelations at various lags should be equal to 0. Okay,
Yes,
so that's
ma'am.
what we're checking.
Okay, okay.
There should be no autocorrelation between the errors at different lags. So let's continue here. Generally, ARIMA modeling is used for forecasting. Okay, but before we do that, I'll quickly show you something else that I prepared. Okay, this I'll show you all this and discuss it in greater detail in the next class, but just focus on this for now. Okay. So in an ARIMA model, the AR part refers to the autoregressive terms, MA refers to the moving average terms, I refers to the order of integration. Okay. So in those characteristic roots, if you remember the first part that we were discussing today, that B gives you the characteristic roots, okay, or L will give you the inverse characteristic roots. If you find that the value of B is greater than 1, okay, it means that the particular time series has a unit root. So those are referred to as unit roots where the value of the characteristic roots is greater than 1, okay, absolute value. So in an ARIMA PDQ model, okay, it will have D unit roots, that particular time series, and that's why you difference the data D times to make it stationary. Okay. For example, in our case, we difference the data once. Okay. We took a first difference once. That's why the order of this small d term was equal to 1. Okay. So whenever a time series has d unit roots, you'll need to difference it d times to make the time series stationary. Okay? If it has 1 unit root, that means that the time series is not stationary and it is integrated of order 1. Okay? If it has 2 unit roots, then the time series is integrated of order 2 and you need to take a second difference. Okay? Or you need to difference your data twice in order to make it stationary. So that is how this whole term or abbreviation is coined. And once you difference the data and make it stationary, the process is called a difference stationary process. Okay, we'll be discussing this again in the next class. But for today, we'll move on to forecasting. Okay, so most of the time, ARIMA models are used to forecast future values of the particular time series. Okay, apart from generating the model with the best fit and trying to describe the data that you have itself, you might want to forecast the future values of the time series, and ARIMA modeling becomes very important there. Okay, so it is one of the most frequently used forecasting techniques. So in many cases, you will find that once you're right out of college or the university, you might end up doing a job where you're doing forecasting using ARIMA models. Okay, so let's try and learn the forecasting part of it. We don't have too much time, but I'll just briefly show you what we do here. I'll just describe it to you first, and then we'll go into the theory of it in the next class. Okay. Now, when you are forecasting, okay, there are two things that you can do. One thing is that you can generate one step ahead forecasts, okay, or you can generate multi-step ahead forecasts. Okay. So for one step ahead forecast, just think that you have maybe, let's say, 200 observations. Okay. So your time series has 200 observations, and you estimate a model using only 150 observations. Okay. If you use all 200 observations, then you can forecast the values in the sense that the estimated values of YT, okay, suppose YT is your time series, then the estimated values of YT will be your forecast values if you use the entire 200 observations, and that is called in-sample forecasting. Okay? So you're forecasting within the sample. So once you get the estimate of YT hat, you can compare the actual value with the estimated value. So YT minus YT hat will give you your errors. Okay? So you'll be able to understand how much you've not been able to forecast or to what extent this particular time series has been unforecastable based on the values of the errors that you're getting, whether they're very large or not. So one thing you can do while forecasting is in-sample forecasting, which is what we have done here. Okay? So you can take the entire time series, estimate a model, and then compare the value of the estimated time series, YT hat, with the actual values, and then get your forecast errors from there. Okay? Or you can leave out a portion of your data, okay? Which is, if you have 200 observations, maybe you can fit the model for 150 observations, okay? Estimate a model using 150 observations, and then after that start generating forecasts. Okay, so you could either generate one step ahead forecast or multi-step ahead forecasts. Okay? So first I'll discuss one step ahead forecast. So now that you have estimated using 150 observations, then what you can do is just predict one step ahead. Okay? So predict for the 151st time period what the value of YT is likely to be, and after that again estimate the model, okay, using this time 151 observations. So keep rolling your sample forward by one at every step and generating one step ahead forecast. For example, use 150 observations and forecast the value for the 151st period. Okay? Then increase your data set by 1. This time use 151 observations and forecast for the 152nd period. Okay. Then again roll your sample forward. So use 152 observations this time and forecast for the 153rd period. So at each step, what you're doing is increasing your sample size by 1 period and you're forecasting 1 step ahead. Okay. Then based on the actual values, since you have all 200 values of the time series, you'll be able to compare the actual values with the forecasted values. Okay, so you'll have 50 forecasts here. If you keep doing this, you'll have 50 forecasts until you reach the 200 time period. So you'll be able to compare the actual values and the forecasts and then decide how good your forecasts are. We'll be discussing measures of forecast accuracy in the next class. Okay? So that is one way to do it, to generate 1 step ahead forecast. I hope you all have understood this. Anyone has any doubts?
Can we pause for today, ma'am?
Is everyone tired, or can I just finish at least describing this and we'll generate a few
Ma'am,
forecasts?
let's do it in the next class. It's been too hectic.
Okay, fine. All right, so then we'll stop here for today's class. One thing you all can do is just to practice, I had sent you one data set, right? I had emailed a data set to you all.
Yes, ma'am.
Okay, so if you open that data set, it's a data set on residential property prices. Okay, it's residential property prices for India. So you can practice using that. Okay, so this is the data set I've sent you, time. So this, if you look at it, it is quarterly data. Okay, and these are residential property prices. Now I'll show you the actual data set. Okay, so if you're able to see this, this is residential property prices for India. Okay, it's quarterly data and it is not seasonally adjusted. Okay, so just keep this in mind. What I want you to do is, instead of taking the prices itself, calculate the log returns. Okay, you can do that in Excel or in R. It's up to you how you do it. So calculate the returns and then estimate ARIMA models for this data set. Okay, and come up with the best fitting model. We'll discuss that in the next class. Is that all right?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. And one more thing that I needed to discuss with you all was about your practical assignment. Okay, so instead of your first periodical test, you're going to have a practical assignment. So for that, how much time would you all like to actually do the practical work to submit your assignment?
Ma'am, please consider that we also have our interviews and our case study thing going on in first week of October, like 4th, 5th, 6th in line. So if you can just adjust for like give us ample enough time so that we are able to do the project also and we can able to focus on the placement also. So I think 10th October would be uh, a sufficient time for everyone to submit and actually do their project.
10th October, starting from when? That's what I want to know.
Ma'am, you can send the
Like, do you need a
assignment
week's
today.
time or? Okay. What I thought is I will not send the assignment because I can already guess what will happen if I send you a data set. So instead of that, what I want you all to do is search for data yourself. Okay, so you can check Fred, okay, which is this particular database that I had used. You can type Fred or you can use RBI data, you can use Yahoo Finance data, any of these things. So download some data, okay, time series data itself, and then estimate a model using that. And what you can do is create a Google Sheet, or I'll create it for you and share it. Okay, so what you need to do is type in your name, roll number, okay, and I'll probably fill in that Excel sheet with some column names. So what is the data that you're using? Okay, very briefly. For example, if it's residential property prices, just type that. Then what is the frequency of your data? Is it monthly data, quarterly data? What is the source of the data? And then when you are submitting your assignment, okay, you can share both the commands that you have used and the data set itself, okay, so that I can run the code and check what results you're getting. Okay, so what you need to do is when you're submitting your assignment, share the code, share your conclusions from whatever you've done, okay, and share your data set. So when you're saving your data set, if you have saved it in an Excel file, name it with the roll number. Okay, your roll number will be how you name your Excel sheet. And no two people should be using the same data set. Okay, just to make sure that there's no copying and everyone does their work on their own. Okay, so make sure that each one is using a different data set. Based on the Excel sheet which I share, you'll be able to see who is doing or using what data, so you don't repeat it. Okay? So we'll go about it that way. And I'm guessing you want time from now till October 10th. Right?
Okay, ma'am.
Yes, ma'am.
Okay. So what you can do is, for this, just estimate the ARIMA modeling, a model part, and since you have time till October 10th, in the next class, I'll do the forecasting part of it. So you can generate the forecast also, and that entire thing, ARIMA modeling plus forecasting, will be your assignment. Okay? And you'll have time till October 10th for that. So I hope that's fine with everyone. We'll stop today's class here. Just go through whatever we've done today and see if you have any doubts or questions for the next class. Okay, so we'll meet next Friday. Till then, you can start working on your assignment, download some data and start estimating ARIMA models. All right, thank you for your time. We'll
Thank
stop
you,
here
ma'am.
today.
Thank you, ma'am.
Thank you, ma'am.
Thank you.
Thank you, ma'am.
Thank you, ma'am.
Welcome.